ago, we started Ethereum Singapore, and we brought the Ethereum Foundation all the way from London. About 65 people turned up sometime last year in late April, and this year, in 1 year's time, we are currently the largest Ethereum meetup group across Asia, and the largest one. And we're very fortunate. The president and founder here is Vitalik, and I believe that he has a lot more to say. So, ladies and gentlemen, please welcome Vitalik.
Thank you. So, since this is an actual Ethereum meetup, I can assume that people know at least something about Ethereum. So, how many people here know what a Oracle tree is? Okay, cool. So I think what people wanted me to talk about is probably primarily the kind of research and development roadmap that we have for the project, which I probably have talked about in many places in detail, but at the same time, it is something that I get changing fairly rapidly, and it's also something that's worth kind of talking about often, as there's kind of a lot to talk to, and quite often I just sort of approach everything in one place. So I think in general, also the first thing that I'll start off with is just by covering the kind of major research sources that we have. So we, in general, spend a lot of time talking to both applications, users, developers, and in general, we see about 3 or 4 primary sort of challenges in blockchain technology. So these are basically look at, what would a kind of perfect, absolutely sort of utopian, decentralized platform look like? What is Ethereum now? What's it yet? And I think the 4 major categories are number 1, scalability, number 2, privacy, number 3, latency, and number 4, account security. So I've actually very conveniently kind of arranged them in actually descending order of difficulty. And another sort of quick one in there is kind of blockchain energy consumption, which is one of the main things that we're proof of stake. So I'll probably put that as kind of number 1.5, somewhere between scalability and privacy as far as capability goes. So in yesterday's presentation, one of the kind of sort of major themes I had at the beginning is I talked about the blockchain stack as being kind of made up as a sort of collection of layers. So basically, in general, with blockchain protocols, it's kind of like the internet protocols. You have kind of things built on top of more fundamental things, and then on top of those, you have higher-level things, eventually sort of branching out into areas of applications and individual applications and then actually companies. So, or nonprofits, or just individual developers building things and ultimately users. So we have, at that sort of very lowest level, the way I see the ecosystem is basically that level 1 is kind of the actual blockchain protocol. So it's things like Bitcoin, things like Ethereum. Also, even aside from blockchains, there are also kind of other protocols that aren't blockchains, but probably have roughly kind of the same height in terms of how abstract they are. That include probably IPFS on that somewhere status, that includes Swarm, that includes Whisper. So in general, kind of extremely abstract kind of base layer technologies like that. Turned off the music. So I think that's kind of the first layer. Then on top of that, probably the second layer is essentially kind of middle layer tools. So this would include high-level programming languages, tools for building smart contracts, user interfaces, developer interfaces, even sort of smart contract systems sitting on top of Ethereum that other smart contracts will need to interact with. So if you look at even something like Digix, on the one hand, Digix Code is an application. You can buy Digix Code, you now have a piece of code on the blockchain. But at the same time, it's also something that it's not just for people to use what has to store value as a currency. It's also something that you can use as collateral inside of another smart contract. It's potentially, the DAO might end up buying Digix Code at some point. Maybe it should. At some point, maybe you might have financial contracts that settle in Digix Gold. You might even have applications that look at the price of Digix Gold compared to Ether. So it's one of those kind of things both an application and something that can sort of very heavily interface with everything else. Aside from tokens, there's also identity systems, are sort of similarly fundamental. Data sources, Oracle data sources for smart contracts, similarly fundamental. If you want to have a financial contract based on the price of gold, you need to have someone tell you what the price of gold is. So that's part of the second layer. Then also privacy preserving technologies. Just to skip straight ahead to number two, which I think goes to number three, because number two is now under stage. So privacy preserving technologies is something that maybe theoretically could be handled at number one. So like the theoretical sort of holy grail would be a platform where you actually have a decentralized system that sort of looks like a black box by default, except it does give you like absolutely strong cryptographic proofs and evidence of specifically the things that smart contracts wants to provide in outputs. So something that's completely black box where people want it to be a black box and which offers infinitely strong authenticity guarantees in place where people want that. Problem is actually implementing that is pretty much impossible. Now you can get pretty close with things like authentication, with things like homework encryption, with extremely like crazy things like Greg Maxwell calls pretty bad, but it's even still it's not really perfect because you could still sort of break those systems or potentially attack them by doing things like simulating like say blockchain history and doing a bunch of attacks against them. So actually having an entire sort of blockchain-based layer that sort of fully preserves privacy, I think is not going to happen. What we can do is we can create a bunch of systems that sit on top, a bunch of systems that provide privacy for specific applications. So one of those sort of holy grail kind of god technologies that I talk about is Digix. So basically generalized zero knowledge proofs. So this basically means that you can prove any kind of mathematical statement about some number that you know, prove that statement is true, prove that you know the number, without revealing what the number is, or without revealing any other information. Actually, potentially quite powerful. So one practical example. Let's suppose that I have some kind of equity crowdfunding application. Let's suppose that for legal reasons, my lawyers tell me that I want to accept people from every country except for the US. So here's what I do. I take a bunch of identity systems, potentially something like custodian e-residency, potentially some kind of phone number verification, potentially, consensus proof of address verification, maybe some other government IDs. And I create a system where in my sort of contract that issues shares, if you send in Ether, the contract only actually does that if it includes a zero knowledge proof that basically says, I possess pieces of information that basically are cryptographic certificates from some entities saying that I'm a citizen of some country other than the US. So basically take the zero knowledge proof, you would pass it into log as a transaction. Smart contract to verify the zero knowledge proof. If the proof is correct, then we give you the shares, otherwise we should refund your money and say, well, no thank you. So the nice thing about the zero knowledge proofs is you can do that without actually revealing any other thing about your identity. The only thing you actually need to reveal is the very specific fact that the verifier of the proof wants to verify. You could potentially verify that you're a citizen of some particular country. You could verify that you have some kind of credit score according to some credit system. You could verify that you are a unique individual, like in some sense. So there's huge amounts of potential and basically at the same time getting extremely high degrees of kind of authenticity and security, but preserving privacy at the same time. So applications will know exactly what they need to know and absolutely nothing beyond that. So that's something that's really cool technology, and it actually is a very nice complement to blockchains. Basically because blockchains provide authenticity, zero knowledge proofs provide very strong levels of privacy. If you want both, you can kind of slap them together. So there are many classes of applications where if you just make zero knowledge proofs verifiable inside of smart contracts, you have a very powerful and versatile privacy solution on the blockchain already. So there's a platform called Hawk that was developed primarily as a white paper by Andrew Miller and by a couple other researchers. And the idea there was basically that if they introduced this kind of notion of a sort of private contract. And a private contract is kind of like a smart contract that has some number of participants. but the state associated with all the participants is encrypted. So then the idea is that it's all encrypted and then there is kind of one particular party which kind of is a manager. Now, you could even have like you could even have a system where you have like each user kind of being the manager of their own data. You could sort of architect it in different ways. But the idea is that if you want to update the contract, what you would need is this sort of manager would create a kind of zero-knowledge proof that says, here is the old state of the contract, encrypted. Here is the new state of the contract, also encrypted. And then, by the way, here is this magic zero-knowledge proof that basically states that I know that this new state is the correct encrypted result of applying the encrypted transaction to the old state. So everything is still encrypted, everything that gets published on the blockchain is still encrypted, but because of the zero-knowledge proof magic, basically we have full authenticity. So that's something that, for example, could be built on top of Ethereum and could actually make the platform, potentially extremely powerful. Zero-knowledge proofs are really cool technology. They do have their drawbacks, so the math is very complex. It's also the sort of thing that also has some technical challenges. So one of the major ones is that even though verifying a proof only takes 6 milliseconds, creating a proof actually takes about 90 seconds. So if you're a startup, one possible opportunity, by the way, is to basically create a kind of USB dongle that uses, an FPGA or an ASIC to just accelerate it and let people make proofs much more quickly. So if someone wants a quick business idea and they have context, they can do hardware, there you go. So then, aside from that, there's also simpler kinds of cryptography. So there's ring signatures, linkable ring signatures. There's sort of very limited forms of homomorphic encryption that are still fairly efficient. So there's a bunch of kind of different individual tools that you can combine together that can provide more privacy in specific contexts. Whether it's currency transactions, identity management, the content of sort of the terms of particular like two smart contracts between two individuals, voting. So lots of different applications, they might have their own kind of privacy solutions. And it's definitely one of our goals to kind of work with, both the academic community, application developers, sort of higher level kind of programming language developers to see if we can build tools that make these privacy solutions as easy as possible. So that's one thing that we want to do. And we have kind of started doing it. So I've written a piece of sample code that does like ring signature verification on top of Ethereum. We have a sort of proposal for a hard forking change that sort of adds some new opcodes that makes that much more efficient. So it's starting, but still a lot of work to go. Aside from that, sort of still sitting on the higher level, the other major challenge that we have is basically account security. So in the case of blockchains, like there's one kind of security is making sure the blockchain itself sort of continues running, that there aren't any 51% attacks, that the system kind of retains its integrity, that you can't censor transactions. That's all well and good. The other thing that we need to make sure is that basically that even if the system itself is absolutely secure, that the accounts that users use to access the system are also as secure as possible. So yesterday I had a bunch of slides where basically showed some incidents that happened in the Bitcoin community and in the Ethereum community. So actually the big account security losses were more in Bitcoin land, and Ethereum land what tends to happen is smart contracts that have bugs in them. That's also an area of research, and it's one that we really welcome kind of active participation in. So basically the challenge is, let's say I have $500,000 of Ether, let's say another $500,000 of Digix gold, and my login to 100 different decentralized applications, and a bunch of company shares through Autonomous, and a bunch of other things, all in one account. Let's say I lose the private key to that account. By default, I lose access to everything. So let's say the computer that the private key is on gets hacked or gets stolen. The guy basically has access to everything. So how do we make systems where we can avoid those kinds of pitfalls of security, but without just bringing centralization right back in? So there are approaches. So one of them is this concept of multi-sig, where instead of having one key control an account, you have kind of three of these, and you need two of them in order to send transactions. That's kind of interesting technology. There's obviously work to do in making it more user-friendly. Another option is hardware wallets, and these are mutually exclusive, so I think hardware wallets should be used as part of a all-encompassing solution, not as the only thing. There's various different approaches involving kind of two-factor authentication. There's obviously hardware dongles that have different kinds of access controls on them. There's different ways of kind of presenting the information to the user. So I think there's a lot of kind of innovation still to be done in that sector. Now, just to sort of expand on that sort of sector a bit more. So we've already had Bitcoin wallets for about 3 or 4 years. Either Bitcoin hardware wallets, Bitcoin multi-sig wallets. So the industry of protecting the security of people's Bitcoins has existed for a while. Now, I think the solutions so far still aren't adequate, but even still, there's still a bit of work. Now that we're moving from just talking about Bitcoin and just talking about cryptocurrency to talking about Ethereum and general purpose decentralized applications, the security situation becomes more interesting. One of the reasons why is because when we talk about currency, it's easy to tell what's a tiny amount of money and what's a huge amount of money. When we talk about general purpose applications, let's say some application requests to use your account to send a message from account number 0xDB1C to account number 0x5837 with 0 Ether and with data 0x7EB5 7C14020 blah blah blah. You see this? How do you know? Now the application itself tells you, well, okay, all you're really doing is you're just uploading a post on decentralized Reddit. What if what that message is actually doing is stealing all of your Digix coins and sending them to some attacker? So that's not something that you can kind of figure out sort of a priori. That's something that's really a matter of kind of how do you actually figure out what's less valuable, what's more valuable, and how do you present that information to the user? How do you make sure that the user experience is actually one that makes it more convenient to send things that are lower value, but that actually requires more friction to send things that are higher value so people don't make mistakes accidentally. So those are all areas that need sort of a lot of research, need a lot of experimentation. Business idea number 2, solve the problem. And by the way, please do it in the same USB device that generates the zero knowledge proof, so I don't have to carry 2 USB devices. So then that's account security. Now let's talk about latency. So basic problem, Bitcoin block time of 10 minutes. Now these days we have the block size debate, so thanks to the wonderful innovation of the block size limit, some people are apparently experiencing confirmation times of 20 to 30 minutes. But even still, even if you go down to 10 minutes, even if you go all the way down to the 14 seconds that Ethereum gives you, even still for many applications it's not enough. It's still, people basically who are using web applications want some notion of instant feedback. So that's something that blockchain protocols currently don't really provide well. Now, one thing that we're doing is we're trying to make Ethereum blockchain itself as fast as possible. That's good. Another thing that we're looking at in parallel is essentially protocols on top that try to provide sort of instant finality for some applications, even if the underlying blockchain layer is small. So if you brought up payment channels, state channels, lightning networks, we're looking at sort of that kind of technology and seeing if we can make it sort of as widely applicable for as many classes of applications as possible. So where does latency matter? Number 1, retail payments. So if you're making a retail payment, you want it to be confirmed in 14 seconds is too long. You want like 1 or 2 seconds. Number 2, IoT applications. So 2 years ago, IBM wrote a white paper to talk about democracy of devices. They talked about how you can use Ethereum as a kind of platform to allow devices from different companies to talk to each other. That's all wonderful. You have a gig, instead of living in the Apple house or the Samsung house, you still get to live in a decentralized house. But problem is, IoT, when I talked to Huawei about this idea about a year later, they brought up latency. Basically said, okay, well, we want these devices to talk to each other in 200 milliseconds. You're saying your blockchain has a block time of 14,000 milliseconds? So it's important to say 14,000 milliseconds. Milliseconds aren't even as people think yet. So we clearly need to come up with something fast. Number 3, any kind of decentralized exchanges. So I think in general, I am very interested in the notion of decentralized cryptocurrency exchanges because I think centralized exchanges are terrible the fact is, these are crypto assets. If we can exchange them in a decentralized way, we really should be. Personally, I hope all these sort of centralized crypto-to-crypto exchanges go die in the next 2 years or so. So, investment opportunity, number one, short, and number two, donate to create a decentralized one. So that's, but at the same time, there are real challenges in actually making the platform performance enough that people are willing to actually trade on them. So, like, we see the gains, we see that, you can get rid of cryptocurrency hacks, get rid of like 95% of the consumer protection problems in the crypto exchange industry. Even in the case of fiat to crypto exchange, you can actually replace exchanges with centralized intermediaries that just provide sort of backed tokens, and then you make the exchange between like backed tokens and Ether or whatever else on the blockchain. So even there, you can knock down. The fact is, at least like 90% of cryptocurrency exchange losses are on the cryptocurrency side; they're not on the fiat currency side. So if we can make at least the cryptocurrency side decentralized, we can knock down the losses from that to about 90%. Of course, a lot of those steps are actually technically fraud because the exchange is feeling different themselves, but same thing. So problem is, number one, we more latency. Number two, probably more scalability. Number three, obviously we want to deal with issues with miner front running, but at the same, so I think there is a lot of potential, but at the same time there are a lot of challenges, and latency probably is one of them. Now I will say that they're actually already, even on top of Ethereum, there is kind of one decentralized exchange that's already running. There's the Maker OTC, which is that already has some pretty good sort of trading between Maker coins and Ether going, but it's still an area that needs a lot more sort of growth. There's identity applications, probably a bit less important, but even still, just from a user experience standpoint, if they're just 1 second is so much better than 14. But people are willing to tolerate 14. Like, if you look at something like traditional DNS, when you buy a domain name or update some settings, people often have to wait up to a day for everything to be confirmed. So, if we can knock that down to 14 seconds, then I guess that might be good enough. So now we talked a bit about privacy. Next item on the list is, of course, proof of stake. So, see, I've talked for about 20 minutes right now. Unfortunately, these next sections are going to be a bit longer. So, in general, why do we care about proof of stake? Simple answer is bunch of reasons. Number one, Bitcoin mining right now burns about $600 million a year. If you include environmental externalities, if you include government subsidy costs on top, chances are the total cost of society is somewhere around $1.2 billion a year. So if we can come up with a consensus algorithm that doesn't have those costs, then chances are we can actually, number one, not spend as much money on electricity, and number two, save the environment. Yay! That said, according to Donald Trump, the environment isn't a problem. So the way the proof of stake basically works is the way, as I described it, it's kind of like virtual mining. So take proof of work. You have $1,000. Use your $1,000 to buy a computer. Plug the computer in, download the software package. That computer will now crank out blocks from time to time, and you get mining rewards from time to time on some random schedule. Take proof of stake. You have $1,000. Use those $1,000 to buy $1,000 of Ether. Inside of Ethereum, you have a mechanism by which you can convert your 1,000 Ether into a virtual miner. Then the virtual miner there are more rules in the protocol that basically simulate the virtual miner having the right to crank out blocks and give you a block reward from time to time. So the baseline is you simulate a similar process, but without the cost of the electricity loss. So the nice thing is, on top of that, you actually have other benefits. So one of those benefits is the concept of finality. So with proof of work, the only way that you can incentivize people is with rewards. With proof of stake, you can use rewards and you can use penalties. So the original proof of stake developers didn't actually even realize this point. This is why people back in 2011, people talked a lot about proof of stake, about nothing at stake, like it was a fundamental with the early proof of stake protocols, they used rewards, they didn't use penalties, they didn't even use the implied penalty that proof of work has, which is the electricity cost that individual miners use. In reality, you can engineer protocols that have penalties that are as high as proof of work and potentially millions of times higher. You can literally create a protocol which is the equivalent of, imagine a version of proof of work where if you participate in a 51% attack, your ASIC mining farm burns down. So imagine how much more secure proof of work would be if that was the case. Well, guess what? With gas projects. So that's the second thing. Third thing is, I think it offers a lot of opportunities to kind of re-engineer the mechanism so that you have, number one, in general, faster block times, more efficiency, even some sort of moderate gains in scalability, lots of sort of other benefits. So even one of the other pieces of research I'm looking at is this is somewhat more academic, but basically a sort of version of proof of stake kind of NXT style consensus that is converges in a kind of subjective partial synchrony model, not just sort of synchronous network. So what that basically means in sort of less easy terms is that even if the network runs much more slowly than you expected, the thing is still guaranteed to converge and just converges more slowly. So the reason why that's nice is because if you have that property, then suddenly you can be a lot more aggressive in what the default block time is. So you don't have to say 14 seconds, you can knock it straight down to like 2 to 4 seconds. So that's basically, if any of you follow our research chat, that's basically the reason why we care about that so much. So in general, we kind of see, over the past few months, we've been doing kind of a lot of like very heavy research and kind of mapping out the proof of stake design space. Another probably-ish thing that we've realized is that we were looking at everything ranging from algorithms that were kind of inspired by traditional proof of stake algorithms, so PureCoin, NXT, Vitalik, DeFox, and more kinds of approaches, and algorithms that are inspired by traditional Visa-King fault-tolerant algorithms, DLS, PBFT, everything in that category. So the thing that we realized is that algorithms in the second category, they do have nice mathematical properties in terms of being able to kind of formally prove that they work, even if anywhere up to a third of the network is faulty. But at the same time, they have the problem that they don't scale well to large numbers of nodes. So if a lot of people you might have heard some complaining on the forums that why does Casper have a limit of 250 validators? Well, the reason why we had that limit in the initial versions is because we were exploring algorithms that looked more like these traditional Byzantine fault-tolerant algorithms. Right now, we're looking much more at sort of more blockchain-style algorithms, and those have slower convergence properties, but the benefit is that you can support an unlimited number of validators again. Because no matter how many validators there are, at the end of the day, there's only one validator that gets to create a block for each block. So that's something that we're kind of looking at as well, mapping out the design space heavily. Also looking at kind of random number generation and proof of stake. So the other kind of major category of attack that people who kind of aren't too well informed about the issue sometimes deal about is stake grinding. Once again, big issue in algorithms in 2011. In sort of modern proof of stake algorithms, you can actually sort of design the random number generation in a way that actually is much more resistant to grinding attacks. Just as a quick sort of outside use of evidence, you can actually do this. Notice how nobody has ever complained about stake grinding in PBFT. So that's another area of research. In general, our proof of stake roadmap is basically saying, number one, figure out the algorithm, figure out some like basic, do our kind of our own sort of intuitive research, make sure that it's roughly sound. Number two, make a testnet in Python. In parallel, do a bunch of more formal proof on it. If step 2A and step 2B pass, number 3, deploy. Like implement across all the clients and push it out. So that's kind of the progress. Before we talk about scalability, the other issues are there's also the plan kind of Metropolis hardcore. So if you go on github.com/Ethereum/EIPs, see the list of like about 10 to 15 changes that we want to make from the job list. Some of them are kind of fairly technical efficiency improvements. One of the major ones is what we call sort of abstraction. So the idea behind abstraction is basically that right now, there are two types of accounts, externally owned accounts and contracts. So externally owned accounts controlled by individuals, and there's kind of one sort of account scheme that's based on kind of sequence numbers and what cryptography baked right into the protocol for securing them. The problem is that this approach is still kind of inflexible. There are some applications where it actually doesn't really work well. You have to do a bunch of kind of complicated tasks, like you have to have some accounts that just serve as kind of pass-through accounts. Those pass-through accounts have to hold ether in them and so forth. So our approach with abstraction is we want to eventually pull the two categories of accounts into one, just have contracts. And even regular accounts are going to be contracts as well. So regular accounts are basically going to be kind of pass-through contracts. They're going to accept transactions coming in. They're going to check if the transaction has a valid signature. If it does, they're going to strip the signature away, and they're going to sort of pass the transaction along out of the message. So, the way it'll work sort of programmatically is that there's going to be sort of some notion of a kind of global entry point address. From that address, basically, anyone can send any transaction. All transactions will be sent from that address, and then they'll be sent from that address to the account that ultimately is the account that the person wants to send the transaction from. The account itself will do the signature check, it'll pass it through and forward it along and it's good. So the nice thing about this model is we want to sort of Ethereumify account security essentially. So the reason why people like Ethereum in the first place is because everything is kind of so general about it. You can kind of mix and match things in lots of different ways. You have a lot of freedom as to like how you build things out in code. We want to do the same for account security. So if you want to have a multi-sig account, we feel that account should have the exact same sort of status as a regular account does. If you want to have an account that's protected by some kind of ring signature, some kind of crazy zero knowledge proof, we feel that account should have the exact same status as a regular account does. If you want to experiment with like different ways of doing transaction nonsense or sequence numbers, so that you can send transactions slightly out of order, you should be able to do that too. If you really like UTXOs, you should be able to do that too. So try not to really make everything from the protocol kind of as flexible and kind of move it into Ethereum code itself as much as possible. That's the kind of initial step. Later on, our later kind of abstraction roadmap actually is trying to move as much of the Ethereum protocol as we can into Ethereum virtual machine code. So that's kind of the goal. Now, that finally, I guess we get to move on to scalability. So, in general, scalability, big topic in blockchain land, big topic in Bitcoin land, big topic in random 150 different private blockchains land where each one claims that it can do 100,000 transactions a second. So, why do people care about scalability? The answer is pretty simple. Ethereum can do 15 transactions a second right now. If you want to replace Visa, 4,000 transactions a second. If you want to replace the Shanghai Stock Exchange, 80,000 transactions a second. If you want to have an identity system where all 7 billion people in the world send one transaction every day, 7 billion per day divided by 86,400 seconds in one day, that still gets you to basically about 85,000 transactions a second. So, those are the scales that you need to be at if you want to actually create a decentralized base layer for one Bitcoin node. Right now, we're 3 orders of magnitude away from that. Now, there are sort of very partial scalability solutions that can get you kind of a bit further. But at the end of the day, with the way current blockchain technology works, there are very fundamental limitations. So, the fundamental limitation is simple. With the way the current blockchains work, every computer processes every transaction. The obvious corollary of that, the system cannot process more transactions than one single computer. So that's the problem. Now it turns out public blockchains on top of that actually have even more incentive compatibility issues. They have to deal with centralization risks, they have to deal with block propagation issues. Now there are ways to cleverly re-engineer protocols to kind of make those problems not be problems anymore. So that's the first step. So if you do that, you might be able to get from 15 transactions a second to maybe 150 transactions a second. Yay. Fact is, there's still a big difference between 150 and 86,400. Now, next step is actually breaking through the barrier. So how do we make a blockchain where you don't need every single computer to process every single transaction? There are some, now I think there are a lot of designs that try to scale blockchains, but they try to kind of scale them in ways that don't really hit at the core of the problem. So one way not to hit at the core of the problem is sidechains. Problem with sidechains is, okay, fine, they're a good functionality solution. You can now have like assets that can jump between blockchains. They're not a scalability solution. The reason is that if you want the sidechains to share the same source of security, the same miners, the same validators, you still, every single miner, every single validator still has to validate every single transaction in all those sidechains. Basically, if your option A, increase the block size from 1 megabyte to 1 gigabyte, option B, have 1,000 sidechains, each of which are 1 megabyte, practically speaking, there's no difference between the two. You're not really making things fundamentally better. Second bad approach to scalability, let's have 1,000 blockchains. Problem with that approach is, sure, you're increasing scalability, but you're doing so at the cost of reducing security by a factor of 1,000. So basically, okay, you have many more blockchains, but why am I supposed to trust any of them? So third bad way of handling scalability is you try to decentralize or sort of distribute something, but not other things. So there's a bunch of protocols that basically say, oh, we're much more scalable because even though every node has to process every transaction, not every node has to store every transaction. You don't have to store the history. You forget it. You can like forget large portions of the history. Okay, fine. You can get 2x, you can get 5x, you can get 10x. You're not going to get 1,000. In order to get 1,000x, you have to create a system where you do not need every computer to process every transaction. So this is where sharding comes in. So the core idea behind sharding is basically that you create a kind of blockchain protocol where you do not need every computer to process everything. Instead, think of it as putting transactions into groups, and then you randomly assign, let's say, 100 validators to a particular group. Those 100 validators validate that group, another 100 validators validate another group, another 100 validators validate another group, and so you process many different groups of transactions in parallel, and so you actually do have that next higher throughput. That's the long-term vision, that's what we're going for. Now, practical challenges in sharding. Number one, sharding is very hard to do in a proof of work context. So this is another side benefit of proof of stake. The reason is, if you try to actually do that with proof of work, so let's say 1% of miners validate each transaction, 1% validate each transaction, 1% validate these. Let's say I'm an attacker. Let's say I have 2% of the network. Let's say I want to attack one particular transaction, either because I want to double spend it or because I want to give myself 3 points or whatever else. What I can do is I can concentrate all of my mining power on that particular set of transactions, overwhelm that particular sort of cluster of miners, and basically break the system. So in proof of stake, here's why. The reason why I can't do that is very simple. You, as a validator, do not have a choice about which transaction groups you validate. You, as a validator, get assigned transaction groups to validate. And you either validate them, or too bad, you don't get a reward. You don't have a choice which groups to validate. So what's the consequence of this? I, as an attacker with 2% of the stake, do not have the ability to concentrate my sort of stake power on one particular group of transactions. Now, if, let's say, I, as an attacker, have more than about 40% of the stake, chances are, okay, fine, there's going to be some situations where I might get a majority in some particular sort of transaction group just by chance, and I will be able to break the system. But that already is pretty close to 51%. Once the number of validators verifying each individual transaction is large enough, at that point at some point you get to the point where you pretty much have something that's statistically indistinguishable from every node validating every transaction. So that's one of the reasons why we're going for proof of stake. Second major difficulty. Let's say I have 40 coins. I send one transaction that sends those 40 coins to person A. I send another transaction that sends the same 40 coins to person B. if the transactions are being processed by different validators, can you make sure that they don't both get confirmed at the same time? They interfere with each other. So, in order to sort of understand how we solve that problem, you have to actually sort of understand how sort of the sharding mechanism sort of works in a bit more detail. So the idea here is, imagine you actually split up the address space into, let's say, 256 virtual regions. So imagine you take all addresses that start with 00, they're in region 1. All addresses that start with 01, they're in region 2. All addresses that start with 02, they're in region 3. All blah blah blah. All addresses that start with FF, they're in region 256. Now, transactions whose effect is limited to one particular region, so where the sender is in one region, the recipient is in the same region, any intermediate contracts are in the same region, those can be processed in parallel. In fact, these transaction groups, they actually are groups of transactions whose effect is limited to one particular shard, so, or one particular kind of address range. Now, let's suppose that I want to make a transaction from an address in shard A to an address in shard B. How do I do it? So this is where the notion of kind of asynchronous receipts comes in. So the idea here basically is, let's suppose I want to send 50 units of Digix coin from shard number 1 to shard number 145. What I do is, step 1, in shard 1, I destroy 100 Digix coins. Then I generate, that transaction generates a cryptographic receipt that says 100 Digix coins in shard 1 were destroyed, and this is targeted toward shard 145. That's step 1. Now, then step 2, take a kind of verbal proof. Remember verbal trees, you all know about them? Take a cryptographic proof that that receipt actually was created, and then that receipt was confirmed. Take that proof, publish it into shard 145 as a transaction. Now, there's this a contract for Digix gold on shard 145. That contract can interpret that particular receipt, and it can say, okay, looks like there has been a receipt, and looks like 100 Digix coins in shard 1 have been destroyed. Now, therefore, I am going to do two things. First of all, I'm going to instantiate 100 Digix coins in shard 145 out of nowhere, and I'm going to send them to the desired destination address. The thing number 2 is, I'm going to register a record in shard 145 stating that that receipt has been sent. So if someone tries to claim that receipt again, well, guess what? It's already been spent. Second time, it's going to pay. So that's the basic mechanisms. 2 steps: separate the debit and the credit. So step 1, the debit happens just in shard 1. The credit happens just in shard 145. The communication only happens through the kind of the root hash of the entire verbal tree. So through the kind of root hash by which the thing that basically the proof of what happened in shard 1 is actually anchored to, and the shard 145 is kind of anchored to as well. So that's the basic idea. Now this is a mechanism you can actually extend going far beyond just coins. You can, in general, you can think of it as a way of kind of creating a kind of asynchronous programming language where you can make any kind of like